Alrighty, let's come back together and talk about these two problems, because what I saw walking around with the groups are a lot of good things, but a couple common mistakes. So let's get the mistakes out of the way first. Converting inches to feet. Yeah. 13.6 inches, or sorry, 13 feet 6 inches is not 13.6 feet. Because there's 12 inches in a foot, not 10 inches in a foot. So my recommendation would be what other groups did, is instead of playing around with that and figuring out, well, 13 feet 6 inches is 13.5 feet, and 3 feet 8 inches is 3.6666 feet, is just convert everything to inches. It's easier that way. Okay, so let's start with the Hot Wheel problem though. So we've got this Hot Wheel that's smaller than the actual Corvette. So anything that you measure on the Hot Wheel should get an answer smaller than the answer on the real Corvette. How much smaller? Yeah. 64 times smaller. So we can do this one of two ways. We can say that the Corvette is 64 times bigger than the Hot Wheel, or the Hot Wheel is 1/64 times smaller than the Corvette. Okay, that number is what's called a scale factor. You've heard that term before, right? Yeah. Okay. So if you build, let's say, if you go to the store and buy a model of a B-52 bomber and you build it, you're not going to build a 1-to-1 scale B-52 bomber. It'll be like a 1/100th scale. Tells you how big it is. If you want to impress your friends at lunch today, fire off the term ratio of similitude. I dare you. Now, many groups figured out that relationship for the Hot Wheel and the Corvette was 64 times. And some groups use that to solve the problem. Like, did you guys use that? Yeah. All right, so tell us what you did.
So when we found out that the scale, like the bigger one was 64 times bigger.
Right, and I assume you did that by taking 32 divided by 0.5?
Yeah.
To get that it's 64. That's our scale factor, okay.
And then we took the height of the car, which was 48.6, and we divided that by 64, and we got 0.76 inches.
Okay, so the question I asked their group was, well, what if I gave you a measurement on the Hot Wheel? Would you also divide by 64? And the answer was?
No, you'd multiply.
You'd multiply. This method is solid. I personally don't like it because when we get into non-real world problems, like for instance, you all know that the Hot Wheel is going to have smaller measurements than the actual Corvette, and that Roger is going to be smaller than the flagpole. However, when we get into weird things like just plain old triangles where they're not tied to the real world, this can sometimes get confusing as to whether or not you should multiply by that scale factor or divide by that scale factor. But again, with a lot of the things that we've done, if it works for you, then stay with it. There is another approach to this, and I don't remember what group. Molly, did you do it?
Yeah.
What did you do?
A ratio. Wait, what's this? I did a ratio? Oh, I did 32 over 48.6, and then I did 1/2 over x, and I just multiplied.
Those are two ratios that make up a proportion. Okay. So I like this method better because it removes that idea of having to multiply or divide by the scale factor. The scale factor is already worked into the problem. So Molly, you chose to do the tire of the Corvette over the height of the Corvette equals the tire of the Hot Wheel over the height of the Hot Wheel. Mm-hmm. Right. Could you do it a different way?
Yeah.
You could flip it, right? And we did this when we did proportions. There's a lot of different ways you could rewrite that. The checks and balances for you here is the following. The tops have to match, and see, it's got to match vertically and horizontally. What do I mean by that? Well, that means that if I go across horizontally, that's tire to tire and height to height. If I go vertically, it's Corvette to Corvette over Hot Wheel to Hot Wheel. If those horizontal and vertical things don't match up, then you're going to get a ratio, or sorry, a proportion that doesn't work. And you also want to use some checks and balances when you're done, that if you solve the Hot Wheel and the Hot Wheel turns out to be 14 feet tall, you probably did something wrong, even though that would be a super cool Hot Wheel. Okay. And Molly, answer?
0.76.
Kayla, same thing?
Yeah.
0.76. Okay. Also, very important, what are the units on this? These are inches, correct. So you're going to see a much bigger emphasis on units here because we're going to get into problems where you can solve it by converting, you can solve it by not converting, and I want to be sure that you know what you're talking about. Is that 0.76 feet, 0.76 inches, 0.76 miles, whatever it is we're talking about? Inez's question.
If it was inches, wouldn't you have to have 48.5?
Because it's already.
It says
It's already in inches.
okay. Any questions on the Hot Wheel? Okay, good.
You're not ready.
I like how I had it.
I like how I had it first.
Flagpole. So, I don't know if it was here last period, but some people were trying to turn this into a mountain problem. Remember those hideous mountain problems we did? Lil just took the words out of my mouth. Why would you want that? This is two separate triangles. Okay. Now, some of you did it as a triangle inside a triangle, which is okay, but the easier approach is to just draw two separate triangles. So we made some assumptions. Sorry, you made some assumptions about this problem. Kev, what did you assume about this problem? This is a fairly subtle point, and you may not even realize you did it. What can you tell me about those triangles?
I'm not sure.
Okay. Yeah, we assume that the flagpole is perpendicular, and we assume that Roger doesn't have one leg shorter than the other. Okay. So we assume they're right triangles. Hold on, I forgot something. Let's go back a slide. Let's get some terminology under control here. We've got this idea of scale factor and ratio of similitude. However, we also are dealing with something called similarity. And I mentioned that word already. By definition, I could give you a fancy math definition, but we're going to use the KISS method here. Same shape, different size. And you recall way back in August when we started talking about congruency, we had congruency defined as same shape, same size. This is same shape, different size. The same shape thing is what's important. Notice I didn't do a 68 Corvette compared to a 57 Chevy. That wouldn't work. It's got to be the same shape. Now, and a new symbol. Okay, it's the top of the congruent symbol without the equal sign. So we would say the Hot Wheel, I can spell, Hot Wheel is similar to the actual Corvette. In Spanish, that's called a tilde. Okay? All right, let's get back to this. Kev, let's go back to you. There are my two triangles. What do we know? Good. What else? You got some measurements for me?
It's a 45, 45, 90.
No, we don't know that.
That they're similar.
Good. So that's actually a great point. How do we know those triangles are similar?
They have a similar angle.
Okay, good. So wait, this is important. Kevin just said they have a similar angle. How do we know that? Like, how do I know that this angle is equal to this angle? Sure you do. Now, here's another assumption we made. We assumed that the shadow of Roger and the shadow of the flagpole were measured at the same time of day. Does that make sense why you'd have to do that? If you go outside, well, not sunny, but if you went outside on a sunny day at 9 o'clock in the morning and you measured your shadow, if you came back at 3 o'clock in the afternoon, what can you tell me about your shadow? It's a different light, correct, because the sun moves across the sky. So the assumption here is that we're measuring their shadows at the same point in time, which means that since the sun is in the same location, this angle, let's call it theta, is equal to that angle. Outstanding. That would also mean that the bottom angles, let's call them alpha, would be equal to each other. Now you'll recall when we talked about triangle congruency, we had side, angle, side, angle, side, angle, side, 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 hypotenuse, leg, angle, angle, side. We said that two of them didn't work, right? What were they? Angle, side, side, because you'll make an ass out of yourself. And angle, angle, angle never worked. Okay. Now, all of a sudden, you'll notice, what about those two triangles? Angle, angle, angle. So angle, angle, angle doesn't prove that the triangles are congruent, but it proves that they're similar. Okay, nice. Good job, Kevin. All right, how about some measurements from this problem? What do we know?
Is it okay if we convert it?
I would prefer it that way, but
Okay, so Roger is 72 inches tall.
okay.
His shadow is 44 inches long. And the flagpole shadow is 162 inches long.
62.
2.
Okay, so let's stop here and talk about this. Which one's bigger, Roger or his shadow? Roger. So Roger is bigger than his shadow. So what can you tell me about the flagpole height?
It's gonna be bigger than his shadow.
Good, and that's an important idea because that's another checks and balances when you get done with the problem to see, does this answer make sense? Okay, you can't have Roger being taller than his shadow, but then all of a sudden the flagpole is shorter than its own shadow. It just defies the laws of physics. Okay. So how do we solve the problem? Look,
I set up a proportion.
go.
So 72 over 44 is equal to x over 62 inches plus 162.
So you did Roger over Roger equals flagpole over flagpole.
Yeah,
And then going across, we've got height, height, shadow, shadow.
yeah.
Should work out just fine. Cross multiply and solve, and you get x being equal to, thank you, Lil. 265.1 what?
Inches and then I converted it to
You did, you're feeling saucy, so you converted to feet, which is?
22.1.
Does that seem like a reasonable height for a flagpole? Yes. Okay, it's about a little more than 2 stories tall. What's the matter?
It's X and H.
Oh, I have made an error. There we go, problem solved. Thank you. Okay, so anything tough about this? Seems pretty reasonable. Okay, now a couple things to think about. Number 1, use the checks and balances to see if your answer makes sense. Number 2, make sure before you even start the problem, are these figures similar? Are they models of the same thing? Is one the real world and one a model? Are they things that have the same comparison here that will allow us to set up that proportion? And then you have to decide what's going to work better for you. Some of you are going to want to stay with that scale factor calculation. Others are just going to want to set up a proportion every time. It's entirely up to you. Here's what I care about. You understand the problem and you can get the answer. Be careful on converting units. Problems? Outstanding. Okay. So what we're going to do with this then is look at, your homework tonight involves more real world problems. So converting units on a map, finding the height of a tree, all kinds of different things. Then tomorrow we'll get into a little bit more geometry. So looking at just plain old triangles that aren't tied to the real world. And then today's Tuesday, Wednesday. Thursday, we'll talk about something called FTS, which I'll get to on Thursday, which will start talking about how do the areas of those triangles compare if we know the scale factor between the lengths. Okay. Questions, concerns, anything that's going to cause? Outstanding. Day 1, which I'll unlock in a second.